Dear students, today we will understand the topic entropy, production in chemical reactions. Let us just consider a chemical reaction occurring at constant temperature and pressure. We will first consider simply a chemical reaction. Temperature and pressure are kept constant. Also, we will suppose the surroundings absorb an infinitesimal, that means very small quantity of enthalpy. Suppose we will represent that enthalpy by simply dH. At temperature at temperature T, then we can write a relation dES will be equal to dH upon T. This is equation number 1. Here dES is simply infinitesimal entropy change, and E here subscript E simply means the external surroundings. Further, let DIS be the infinitesimal entropy this is also entropy change, but arising from the chemical reaction. Then we can simply write, we know from the previous knowledge that this total entropy of the system can be split into two terms, that means this dS plus dIS. This is equation 2. So using equation 1 we have then ds infinitesimal change in entropy will be simply equal to dH upon T. We will simply replace the ds value here plus dis. This is equation 3. This equation can also be rearranged. Suppose we will first write dH upon T plus dis, that can be also written as ts, or we can write it as dis is equal to ds minus dH upon T. If we multiply throughout with minus T, we can simply write this relation as minus T. Here it will be minus T, and if you multiply this with minus T, you will see this T and T will cancel, and this minus and minus will be plus here. So we can simply write this simple relation minus TDS will be equal to DH minus TDS. Because this will be plus, so this is minus here, so we will write this. So we will get this final equation. This is equation 4. Now comparing this equation 4 basically result with the thermodynamic relation which we know that small change in Gibbs free energy is basically for a closed system is related to by this term minus TdS. This is equation. So if we compare this 4 with 5, we will find then that this part basically the minus TdS will be simply equal to then dG, because on the right hand side there are same two terms, so we can simply write them minus TdS, but this is mostly here we will TdIS, sorry, so it will be minus DIS, it will be simply equal to dG. Or we can rearrange this also, so we can simply write DIS will be equal to, we will take this minus and T to this side, so it will be minus dG upon T. So this is equation 6. Thus the rate of entropy production is given by this relation. So we know rate of entropy production or entropy production per unit time, we represented that sigma from the, you can follow this from the previous lecture, so it will be equal to DIS per unit time. So simply this is simply the rate of entropy production, so it can be made equal. We will simply replace DIS here, so can be written in this form: 1 upon minus 1 upon t and dg upon dt. So we can write this relation also. So this is equation 7. This equation basically expresses, so this can be basically expressed by saying that sigma is proportional to the decrease in Gibbs free energy. So this is a simple statement which you can make from this equation 7. Okay, because sigma will be equal to minus dg upon t, or you can say simply directly proportional to the decrease in Gibbs free energy. Now we also know from Clausius, according to Clausius, the uncompensated heat, which we represent as diq, is then given by, this is from Clausius. So we will write simply diq will be equal to TdS minus DEQ. This is equation 8. Here this TdS is basically entropy change of the system, and DEQ is heat exchanger with the surroundings. Since we know this DS, that means the total change in entropy of the system, is related to this expression, hence we can write simply DS will be equal to DEQ upon T plus DIQ upon T. This is equation 9. Or we can simplify this relation, or we can multiply throughout with simply by T. So we will multiply simply with T here. It will be T and it will be T. So this and this will go, this and this will go, and you get a final equation which is TdS will be simply equal to dEQ plus dI. So this is equation 10. Now Now basically treating the chemical reaction as an open system containing, suppose, C components. C components, and we will write, suppose gamma is equal to 1 comma dash up to suppose C. We have the well known relation for open system, which is, that means this change in gives free energy for the open system can also be written as now minus SDT plus VDP plus summation. It is now open system, so the number of moles can change, so we will write it as mu gamma and dn gamma. This is equation 11. Here mu gamma is simply chemical potential, of the gamma component, and this ny is simply number of moles of the same component. Now if we take a condition and where we keep temperature and pressure as constant, equation number this 11 can be also written as, so at constant temperature and pressure, so if this is temperature is constant, dt will be equal to 0, this will be also equal to 0, that means this term will be equal to 0 and this term will also be equal to 0. So we will get a simple relation here, that means change in gives free energy at constant temperature and pressure will be equal to summation from gamma mu gamma dn gamma. This is equation 12. From equations 7 and 12, that means for the rate of entropy production we can simply write it as sigma will be equal to dis upon dt, we know in place of, and we will write it as minus 1 upon p summation gamma mu gamma dn gamma upon dt. So this is 30. We have simply put the value of dg at constant temperature into this relation. Okay. So substituting for dn gamma from below equation. That means this equation dn gamma will be equal to nu gamma d zeta. This has been already defined, so we will write it equation number 14. So here basically from this equation. So we have then this dis upon dt will be simply equal to minus 1 upon t, and in place of d n gamma we will write this part. So we will simply write d zeta. Zeta is nothing but rate of extent of reaction basically. So we will write it sigma gamma mu gamma and mu gamma. This is equation 50. So following the order, we define basically the term. We will basically define this term called affinity. Affinity, suppose it is represented by capital A of a chemical reaction. So we are dealing entropy production with chemical reaction, so we will also define for a chemical reaction. That means this affinity A we will represent it by minus summation gamma mu gamma mu gamma. This is equation 60. So in place of minus and this part we will introduce the value of A. Thus from equations 15 and 16 we will simply write dis upon dt. Same this part, this relation will be equal to, and in place of minus and summation gamma mu gamma we will represent it by affinity A upon T, and it will be left with d zeta upon dt, which will be basically greater than 0. Sometimes this relation is also written as, we can simply write dis is equal to A upon T without taking the rate. So we will write then zeta greater than 0. So suppose this is equation 17, this will be then 18. Okay. So the reaction rate, which we will represent with mu only, is defined in terms of extent of reaction. That means zeta, as we'll simply write mu is equal to d zeta upon dt will be equal to 1 upon mu gamma dn gamma upon dt. So it is equation 9. Also, the molar concentration of the gamma component is defined as, that means we will simply write molar concentration with C gamma, which will be simply equal to n gamma upon V. Here this is n gamma is nothing but number of moles of the gamma component. Basically these number of moles are dissolved in volume. Suppose if we take the volume is capital V. Okay, so we can then write the change in concentration or rate of concentration with respect to time C gamma dt can be written as d upon dt, and this component n gamma upon V we can write it as e raised power minus 1 n gamma. So we can simply solve this. First, if we take it as a product, so it will be 1 upon V and differentiation of this first function with respect to time, and then we can write plus n gamma, and from differentiation of e raised power minus 1 we can take the minus 1 here and write v raised power minus 1 and differential of the function. So this will turn out to be this relation 1 upon v dn gamma on dt will be equal to, actually this is minus, so it will remain as minus, so it will be n gamma and it will be minus 2 e raised power minus 2, so we can write it as v square. This is v here, v square and dv upon dt. So this is equation 21. Now we will take a condition here, assuming that the volume remains constant, and if you look closely into equation 21, if volume remains constant, this term will be 0. That means this whole term will be equal to 0. So we can simply write it as dc gamma upon dt will be equal to 1 upon v dn gamma upon dt, which can also be written as, we will introduce the other values here in place of dn gamma, so we will write as 1 upon v nu gamma d zeta upon dt, which can also be written as gamma V upon V. So this is equation 22. Okay. So from equations 18 and 19 we obtain sigma will be equal to dis upon dt, which will be equal to 1 upon t, a affinity nu rate of reaction will be greater than 0, or we can write it as T sigma basically equal to a nu greater than 0. So this is equation 23. Since temperature is positive, so we see that A and nu must have same sign. So comparing equations 23 and below equation, which we write as sigma is equal to dis upon dt, which we have already derived in the previous lectures for system 1 and system 2, that in case of heat flow, entropy in case of heat flow, we derived this relation there, so it is greater than 0. So we will write it as equation 24. So simply we will compare equation 23 and 24 here. So what we find, that the affinity A plays the role of the driving force. That means is 1 upon T1 minus 1 upon T second. In this above equation, that means 24. So from equation 23 we see that the expression for sigma is basically the product of force. Here it is affinity A and the flow, and flow here it is simply nu, rate of reaction. In the next video we will discuss few cases related to this. Okay, thank you.